She's also working on a few other projects that explore signal processing techniques applied to problems such as forecasting California's electrical load demand, cortisol variability with disease, early wildfire detection, and others. And obviously, these are all cutting edge and timely subjects. I think she's a very busy young woman. So, without further ado, I'd like to present Ankita Mohapatra, Professor.
Good morning, everyone. I'm so happy to see you all for the brief moment that I saw your cameras were on. Thank you for turning up to my presentation. I thought for the first duration of the presentation, I could talk more about printed electronics, what they are, and in the last maybe 30 minutes, tell you a little more about how the engineering department is trying to do its bit to combat wildfires. So, well, let's talk about how our body is supposed to work. I'll try to keep this as simple as I can. I'll do my best to not have any technical jargons, but if you have any questions, please feel free to stop me and ask. So, your body has its own immune system. So, due to the COVID pandemic, all of us have heard this terminology like immune systems over and over again. So, the job of the immune system is whenever your body detects any sort of foreign particles, it tags it, kind of like, okay, this is something I don't recognize. And the other parts of the body, let's not go into that technicalities, but the cells that are supposed to protect your body flush those foreign particles out of your immune system. Now, this is great when the foreign particles that we want our body to throw away are viruses or bacteria or harmful stuff like that. The disadvantage is that when you take drugs, drugs are not natural to the body and drugs are also flushed out. Like, for example, a common example would be that any drugs like Tylenol or uh, acetaminophen, for example, their effect ultimately wears away after a while. Now, that is your body getting to work. It doesn't like those particles and it slowly keeps flushing them out. So, when we obviously do not want that, and think about like extreme conditions like chemotherapy patients, their body, when the chemotherapy drugs are injected, their body flushes them out very quick. And also what happens, another problem of these drugs just by eating it, like for example, are side effects. Like you take a drug and maybe skin breaks out or someone is facing hair fall, right? But maybe that drug is not intended to do that. The drug is just a normal painkiller, but it has all these side effects because the drug is getting exposed to the other sides of the body. Again, going back to a chemotherapy discussion, this is what you see there too. Maybe the chemotherapy is intended to treat something like pancreatic cancer, but a big side effect of that is the person might end up losing a lot of hair, which is a very common side effect of cancer of chemotherapy. Now, this is because when the person is injected with those drugs, the drugs keep circulating in the body and affects other parts. So, what we can do, there are two or three ways to solve this. The first way, obviously, would be that you put the drug inside a package, right? And that package, think of it as a capsule, for example, right? Um, and that capsule is implanted close to where you want the drug to act. Like if it is some sort of a palliative drug that you want to be released only close to the pancreas, the surgeon might do a small surgical operation, implant the capsule over there, and then at a later time point, the capsule releases the drug, right? So this is something that happens in medicines that are in capsular form, for example, right? They are released from the capsule only when they reach the stomach, right? Another way of doing this, now, if you talk about the disadvantage of this, once the capsule breaks apart in your stomach, it releases all the drug, right? And you have the same problem again. You have delayed the release of the drug, but after it is delayed, there's nothing left for you to do, right? You again have to take kind of a booster dose after several hours. Now, wouldn't it be really nice that if you had that package respond to an external stimulus? Like by an external stimulus, I mean something like a magnetic field, for example. And only when that package is exposed to that external magnetic field, that is when it releases the drug. And by doing this, what you can do is once the package has been implanted, the moments at which you want the patient to get a drug dose, that is when you start giving the pulses. Like let's say at morning 8 a.m., the person receives a magnetic field pulse. At 12 p.m., he receives a pulse. So from the same package, you are receiving multiple doses, right? The advantage of this is that you have earlier the issue was that the patient was unnecessarily being exposed to a very high dosage of drug, right? Maybe the body needs just, I'm giving you a very abstract example, maybe the body needs only 20 milligrams to not to cure that headache, but because the body starts flushing out all drugs, the actual capsule or the dosage recommended or given to the person might be something like 100 micrograms, right? But now you have the 100 micrograms in a capsule controlled by an external stimulus. And because you have the control of when the drug is being released from this capsule, that same 100 micrograms is now being more efficiently distributed across multiple doses. So the patient's exposure to these medicines are also effectively going down. Two, you are not exposing the parts of the patient that are not supposed to be exposed to the drug. So the side effects are also going down, right? So this was the whole motivation of my research and dissertation. So what we did was that vancomycin is a very common antibiotic. We put it in a drug delivery substrate, which is called DDS for short. Let's refer to it as DDS throughout this presentation because it's quite a mouthful. So the DDS that we were working with is based on chitosan. Now, chitosan is obtained, it's a very inexpensive drug DDS. It's obtained from shrimp. So shrimps have the outer scale on them. And the outer scale, it's a very simple chemical process. Once the outer shell has chitin, something called chitin in it. And once we apply some chemical processes to it, we get chitosan, which is a really nice powdery substance. And then the powdery substance can be mixed in reagents like liquids. And it gives us this, that process is a little long, but it takes like 48 hours to do. So so the chitosan is in the form of small beads. And think of it like a sponge. We put the vancomycin on it. It's like a scotch brite, like a sponge with soap suds on it. So our chitosan DTS was very in the form of very, very small beads. And the vancomycin was absorbed on that surface. And the idea was that the vancomycin would stay inside the DDS and we would implant it wherever it is supposed to go. And then once we give it an external stimulus, the red over here, that is when the drug is released. The reason we chose chitosan is because the body is, although it is a foreign particle to the body, but it is biodegradable. The body does not have a very violent reaction to it as you might expect from other plastic or artificial chemicals. So the graph that you see over here is, I'll talk about these results more. This is from one of our studies. So the blue one is called the control graph. By control, I mean samples that did not receive any sort of magnetic stimulation at all. And the red graph over here are the ones that received the stimulations. So we gave them a magnetic field. The magnetic field was given at hour 3, hour 5, and hour 7. And yes.
Kita, I'm very sorry to interrupt, but I'm on two screens,
Mhm.
and one of my screens is way behind. And I'm wondering if any of our members are experience the same delay. Also, I'd like to remind members that you can view subtitles. So that's helpful in reading some of these difficult words. But could you, I guess, let me know if your screens are running behind the audio. Right now, we should be on the graph entitled Objectives, correct, Ankita?
Yes.
Okay, and my second screen is not. It finally just turned over. So if are others experiencing that problem, could you just put your name in a chat? Okay, so we have one message, screen's fine. It may be my system. Okay, so it appears that it's just my internet. So I'm sorry to have interrupted. Please continue.
So as I was saying, now if you see that after every single stimulation, which is right over here, the normal graphs path is being changed. Like up to this point, the control and the test graphs were following a nice, were in line together. But after the stimulation, the red graph saw a sharp shift, right? And same happens, and then after hour 3 it starts leveling out, and then after hour 5, when we give it another stimulation, it gets another sharp bump, right? So at these points are we are controlling the drug release. And if you compare, this is a cumulative curve, like it gives you the total amount of drug released. From the controlled samples, we were able to get somewhere around, let's say, 2,800 micrograms per milliliter drug out. But from the same drug substrate, when we gave a stimulation, we got like 4,000 micrograms per milliliter out. So this is what I meant by this being a more efficient way of administering drugs to patients. You have the same amount of drug, but it is more effectively being released, if that makes sense. Now, as I was saying, if a lot of this chemistry, I'm an electrical engineer, so a lot of this chemistry was done by my biomedical colleagues, and I'm going to mostly skip it. But this is the structure of chitosan. It is a very nice punch for drugs. It can absorb a lot of drug. Vancomycin is a common antibiotic that is used to treat streptococcal and staphylococcus infection. Now, the normal half-life, by half-life, I mean that if if a patient receives 100 micrograms per milliliter concentration of vancomycin, after how many hours will the concentration go down to exactly half, right? Which is 50. So for vancomycin, it is 3 hours. So after 3 hours, it goes down to half concentration, and it forms an exponential decay thereafter. But we saw that if we put it in chitosan nanoparticles are like really small particles. If we put the if we put the vancomycin in chitosan nanoparticles, the half-life goes down, improves by 2 weeks. That is a very, very big change, right? And then because we first wanted to test with magnetic fields, we put magnetic nanoparticles inside the chitosan microbeads. So these were some of our very previous attempts. The image that you see over here is us trying to make some food, chitosan microbeads with some food dye. Obviously, we were trying to work it out. So there were a lot of failures before we found something that worked. This one was all right, but the moment we started adding magnetic nanoparticles, that's when it went so haywire. Like you can see, this shape is all weird. Now, the interesting thing about how the body works, it is kind of very strange. The body does not like anything that has sharp edges or objects. Like this one has all of these corners and sharp edges. The body will immediately hate it and flush it out. But if I had managed to get the same constitution is in a very nice, smooth spherical shape, the half-life of that would have been a lot longer. Um, Now, the images that you see at the bottom was one of our latest attempts. It is, as you can see, it is very nice. It is very smooth. I strongly believe that the crinks that you're seeing over here are mostly dust particles. But otherwise, it's quite nice and good. So we realized what we were doing wrong is that think of chitosan. Chitosan is just a chain. The image that I was showing over here, right? I needed some sort of a glue to make that chain fold in on itself and form a nice spherical shape. So this one was made with glyoxal. And we figured that glyoxal wasn't a very strong glue, which is why the shape was so weird. But when we switched the glue to PEG DMA, it is another body-friendly polymer. When we switched to PEG DMA 550, we got the spherical shapes. We tried other types of, I call it glue because it's a very generic terms, but it's the technical term for it is called cross-linkers. So cross-linkers are the ones that take the chains and make it collapse in on itself so that you get the ball shape. We tried other cross linkers, like we tried PEG-DMS 750, which is a longer chain, but that didn't work either. So it was, if I remember right, I graduated in 2018, right? So 2 years were spent, almost 2 years were spent in a very frustrating pursuit of which chemicals and polymers would work and which wouldn't work. Now, we are going to, let's talk about the experimental setup. Are there any questions? Yeah. So this is the device that we were using for generating the magnetic field. We have, this is where the sample goes, and this helps us with only tests. So we were going to do only put test tubes inside it. At a later time point, we tried mice as well. The results were slightly inconclusive for that. But anyway, so how this works is that the sample chamber over here has a coil wrapping around it. And you can switch out the coils. And there are certain other electronic capacitors inside that you can also switch out. So depending on the combination of the coils and the capacitors, you can generate various kinds of frequency. So if I remember right, there were 10 available frequencies that you could pick. The first was 109 kilohertz, then 164 kilohertz, 329 kilohertz, and so on, and right up to somewhere close to 1 megahertz. So we decided to go with 109 kilohertz because lower frequencies where comparatively lower frequencies were seen to be most effective at causing a drug release versus something that's 1 megahertz. And the hypothesis over here was, we could not verify it, but the hypothesis over here is that lower frequencies cause structural changes inside the DDS, which is why, because of those structural changes, it causes the drug to be squeezed out. So this was our stimulation protocol. The protocol was quite simple. PBS is phosphate buffer solution. The reason we use so what we do is that we take PBS in a test tube, which was about 2 ml, and then we add our drug samples to it, and then we stimulate it. We use PBS is because the constitution of PBS is very close to the constitution of blood. So the drug release or the profiles that we would observe in PBS would be similar to what we would see in blood. So we start off at this t equals to 0 point. We add the PBS. We waited for an hour. After 1 hour, we stimulated it for 1 hour. And at each of these time points, we observe testing, what's going on. After the 2 hours, we tried longer 19-hour tests. So we added the samples. We waited for an hour, then we stimulated it for an hour, then we waited again, then stimulation, then we waited even longer for 14 hours, and then we stimulated it again. More, we tried several other um, profiles as well. There was a 24-hour profile as well. These were the days that I had to spend all my nights at the lab as well. Then we also wanted to see whether we could, rather than give a stimulation for an hour, we could give stimulation even shorter, like for 30 minutes. So what we did, we added the sample. At third hour, we gave a stimulation for 30 minutes, and then we went to hour 5, we gave another stimulation, and so on. This was the graph that I was showing you earlier. Now for all of this, we observed that at 109 kilohertz, the sample that received the stimulation showed a much higher drug release. So you can see that the blue ones, the blue is the control one. Those are the samples that did not receive any stimulation. So they're somewhere over here. And the red ones are the ones that received the stimulation, they are somewhere over here. So the graph on the left is with, as I was saying before, we tracked several different polymers. The graph on the left is with PEG-DMF 550. The one on the right is with PEG-DMF 750. So that's us trying different crosslinkers to see what would work. So for PEG-DMF 750, there were two things going on. First, we observed that the initial release was very high. If you compare between these two, for PEG-DMF 550, the initial release from the sample was somewhere around 400 micrograms per milliliter. But for 750, it was 1200 micrograms per milliliter, indicating that probably it was letting go of all the drug. Then when we gave a stimulation, the difference between how much drug the control was releasing is significantly lower in this graph than how much the test was releasing. But for PEG-DMS 750, the difference is not particularly significant. And the third problem that we faced was that at the end of this test, the PEG-DMS 750 beads had swollen up by so much that they were almost overflowing its container. But not so for 550. For PEG-DMF 550, the beads seem to be at the same size as it was when we started. So when obviously you're going to go with PEG-DMF 550 because when you implant a patient with something, right, you don't want that implant to engorge itself, like become very large, because that would create a host of other issues. This was the profile that I was talking about. We gave the samples. This was with 4 ml PBS samples. We waited for 3 hours. We just kept testing it at every hour because we wanted to get an idea of how the sample of how much drug was being released every hour. So at hour 3, we gave a stimulation of 30 minutes. Then we resumed our testing, wait and testing. We gave it another stimulation for 30 minutes more. We waited again and 30 minutes more. Now, something interesting happens at all of these points. These bars are standard deviation. So we had multiple samples, and this point is the average, and this whole bar indicates the standard deviation. So there's not much of a difference between the control and the stimulated samples. But at hour 4, if you notice, the control samples released very, very low amount of drug, somewhere around 100 micrograms per milliliter. But the tested samples were released about 500 micrograms per milliliter, which is almost 5 times as high than control. This was something we observed at hour 6 as well. This versus this, and this versus at hour 8, the amount of drug released from the control was almost 0. And yet we managed to get a lot of drug released from the test group because of our stimulation. The p-values, which indicate statistical significance, was very, very low, indicating that without failure, the stimulation is causing a much higher release of the samples. And if you remember, this is exactly the plot that I showed a couple of slides ago. So at these points, we are giving the stimulation, and immediately following this, we are seeing a sharp increase in the amount of drug released. And the total amount of drug that we managed to get out of the control was somewhere around 2,800, and from the stimulated samples, it was somewhere around 4,000. And once we did this, we wanted to try, rather than for one day, we wanted to try recreating the same experiment, but over 16 days. It was a really long experiment. We added the samples, and then we tested every single day. On day 12, after 12 days, we gave it a stimulation. And then we waited again. On day 15, we gave another stimulation. And then we finished off the testing on day 16. Now, what we observed was that on day 12, the control was releasing very, very less amount of drug. And same thing, the tested group, the ones that received the stimulation, released a higher amount of samples than the control. Same thing we observed on day 15 as well. On day 16, when there was no stimulation to both, it seemed that both had exhausted their drug. So there was no point in stimulating it further. Now, why this test was significant is because the dotted line that you see over here is called the minimum inhibitory concentration. When a person has an infection inside their body and they start taking an antibiotic, right? We want the antibiotic concentration above a certain level, right? If it drops below that certain level, then the bacteria that you're trying to fight becomes resistant to that antibiotic. So you always have to maintain that minimum concentration of the antibiotic for it to be effective against the bacteria. And this is exactly what we were seeing. So an antibiotic span usually multiple days, right? So you have this line as the minimum inhibitory concentration above which your antibiotic needs to maintain its concentration. So once you implant the drug delivery substrate on all the days up to day 12, both control and test groups maintained that concentration, which is why we did not need to stimulate it. But on day 12, when we observed that the control was dropping below this level, that is when we gave the test groups a stimulation to bump the concentration back to above MIC. MIC is minimum concentration, right? This is again something that we observed on day 15. Once the value dropped so low that the control sample was not effective against the antibiotic as well, against the bacteria. That is when we gave the test groups another stimulation to bump the concentration back to where it should be. So this is another example of how the patient would, if they use a method like this for antibiotics, they would no longer need to eat antibiotics like orally or through injections. They could just have this patch or this implant, and this implant would continuously keep releasing the antibiotic over multiple days. This is another experiment we did. We wanted to find out whether magnetic field was important for the drug release at all. Like if we take the same samples and put it in an oven for the same temperature, at the same elevated temperature, then would the samples release drug? One thing I forgot to mention, and this might be a good point to introduce it. One question that you probably would have is why magnetic field is causing a drug release, right? So we are DDS, the chitosan has magnetic nanoparticles in them. So magnetic nanoparticles are like small magnets with a north pole and a south pole. right? And then when we give it a alternating magnetic field, so alternating, when I say it's 109 kilohertz, it means that it's alternating, or the direction of the magnetic field is flipping every fraction of a second, right? So now you have an alternating magnetic field, and then you have a tiny magnet with a north pole and south pole. So if what happens is, there are two ways in which this thing can react. Either it can also flip in response to the magnetic field, like when the magnetic field flips, it also flips. Or another thing that can happen is the inertia of this is too high to respond to the magnetic field. So then what happens is, there's something called the magnetic moment. Like, the magnetic nanoparticle has the tiny magnet inside, right? Which gives the magnetic moment. The particle in itself, in the first case when we were discussing it, it's also called the Brownian motion. You may have come across it before. The whole nanoparticle changes direction, right, in response to the field. In the second case, the nanoparticle is incapable of keeping up with the field. So only the tiny magnet inside it stays stationary, but the magnetic field inside, or sorry, the magnetic moment inside keeps flipping direction. That's called Niels relaxation. So Niels and Bohr's relaxation are the two kinds of phenomena that occur that helps in releasing the drug, in ultimately releasing the drug. So when you have the Bohr relaxation, or the Brownian relaxation, as it's called, when the whole bead is rotating itself, or the whole magnetic nanoparticle is rotating itself, it creates a lot of friction with its surroundings. And the friction is dissipated as heat, right? And after all of these tests, we saw that the samples were undergoing an elevation in temperature. The elevation in temperature was still far less than the human body's temperature. So it was still fine. In the second case, when you have the particle not moving, but still the magnetic moment flipping itself, the magnetic hysteresis loss, or the loss that occurs because of the magnetic moment constantly flipping itself, is what generates heat. And ultimately, these highly localized phenomena are responsible for causing drug release. So when we took this, we measured how much temperature increase we noticed in the sample after this, right? And then we put it in an oven to observe the same temperature rise. And what we saw, as you can see in the graph, that when we subject to the samples to the same temperature change, but in an oven and not through magnetic stimulation, there's no considerable higher drug release that we see. So these are our samples before and after stimulation. They still look nice and spherical after the stimulation, which is what you want. Ideally, you do not want the samples to be broken apart after the stimulation. I'm going to, this is just a test. It's just us reiterating the results to be sure that what we are observing is conclusive and agrees with the hypothesis. So we did this 19-hour test. We have blue is the control, the red is the magnetic hyperthermia, and the gray is the samples that went in the oven. I say oven, but it's obviously a very low temperature. It's only going up to 38 degrees Celsius from 22 degrees Celsius. This is what we observed. There was no significant change the only significant change observed was when the samples received magnetic stimulation. Now, this is a general discussion of all of this is just a hypothesis that our chemical department came up with. So they said that we might be observing this change because vancomycin and chitosan both are binding to PEG DMA. And then when we have the magnetic hyperthermia, or when the magnetic nanoparticles are being excited by the magnetic field, these bonds are being broken apart. And when the bonds get broken apart, that's when the drug is released. Are there any questions before I hop on to the next topic? So the next type of stimulation that we wanted to check is electric pulses. So we tested magnetic stimulation, and we now want to test with electrical stimulation. So these were one of our very first prototypes that we used to do that. The circuit was quite straightforward. We had a signal source, the one that would generate a waveform. We had the IDE, the structure that you saw over here. And then we had the oscilloscope. It's like, it's useful for graphing the voltage and the current waveform. So we gave it several different kinds of pulses. We tried with sinusoid, we tried with bipolar rectangular, and so on. Now, what we observed was that 100 hertz was very effective at causing a drug release compared to higher frequencies. So this exactly agrees with what we observed in magnetic hyperthermia as well, that stimulation is causing a higher drug release compared to control samples that do not receive a stimulation. So this is what the waveforms would look like. This is the waveforms we applied, and this is the output waveform for bipolar rectangular. This is sinusoid, and so on. And in this particular case, so we have the control, we have 1 kilohertz, we have 500 hertz. Both of these are bipolar rectangular, and the last one we tried was sinusoid. So in this case, we observed that the lower frequency again, which is 500 hertz and bipolar rectangular, was more effective than anything else at causing a drug release. And this is a very interesting image because it shows how the samples look like after stimulation. So these are the control samples. They're nice, round, and smooth. After stimulation, it seems like a hole was punched into them. So I'm not sure if this is clear or not. Like, this image looks like the shell completely came off from the beads. This also looks like it's letting off some kind of outer shell. This one has a big hole punched through. So this was obviously a very drastic effect. We were excited that something was happening. Electrical stimulation was causing some sort of change, but ideally this is not what you would want to happen inside a test subject, right? And these results, we were excited about these results because in prior literature, no one had reported causing a drug release by an electric stimulation in this way. So we were our lab was one of the first to do that, and we filed a patent on these results. So excited by that, we wanted to make the scale a little larger and also customize the circuit. So for that, my professor had this device that he used to print electronics. And it is just like an inkjet printer, the one that you might have at home. You can design various kinds of inks and put it over here. And the substrate that you want to print on goes over here. And then you can print all sorts of circuits on it. So these were one of the very initial designs that I printed. It was a lot of hit and miss because, so this is designed with silver ink. The problem with silver ink was that it tends to spread. So, which is why you can see that this is all joined. Some of the circuits over here are joined. There were so many things going wrong. But we finally found a dimension that seemed to work for us. And this is the design. So the dimensions was 7.5 millimeter and the width of this finger is 0.6 millimeter. The gap between these two fingers was also 0.6 millimeter. And I was successful at printing that. So this is all printed with silver on polyamide tape. Polyamide is very common electrical tape that you might have lying around your house as well. So I printed this, and what I did was I cut up some PVC tubes into small 1-inch sections, and with silicone glue, I pasted it around so that once I put the chitosan DDS that I was talking to before, it stays inside this containment. Otherwise, it would just spread out, right? We had the same setup, the same circuit as before. So we have the signal source, and we give it stimulation. And this is what I observed. So our earlier tests were only 4 minutes long because we just wanted a proof of concept. So we waited for 1 minute. We gave it a stimulation of 30 minutes. We waited again, and then we gave it another stimulation. And after every stimulation, there was a significantly higher release from the samples that received the stimulation. The only disadvantage of this was that we saw that one side of the electrodes was getting corroded. And therefore it was rendering our samples unusable henceforth, or the substrates unusable after the second stimulation. So we increased our sampling, and we now wanted, rather than 4 minutes, and to make it more practical, we now tested for 1 hour. So we gave it a sample of PBS. We waited up to around 43, 44 minutes. We gave it a short stimulation, and then we finished off the test for 60 minutes. And then we saw that in response to the stimulation, the test group was releasing a higher amount of drug. Now, the only disadvantage, as I was mentioning before, is first, the circuits were printed with silver. Silver is not particularly friendly to the human body. So this is not something that we could have implanted inside an animal like a rat. So we were not able to do in vivo tests. The second issue with that is we would want something like gold. Gold is very inert to all sorts of living creatures, right? But we were unable to obtain an ink, a printable ink made with gold. The problem is that gold is so inert that it doesn't want to stick with anything. So that's why we can't print it. And the third problem was that silver, as you can see over here, silver got corroded and started peeling off after some time. These were the images before and after stimulation. This is before stimulation, and these were the electrodes, the blackened electrodes that I was showing you all a while ago. This is what it looks like under a scanning electron microscope after stimulation. So you can see that the silver is starting to peel off here and here, all over here. And the silver is peeling off because at that particular electrode, which is the anode, the silver starts oxidizing, and the silver oxide does not stick to the substrate. So these are some reactions. I'm going to skip this because it's very technical. So this finishes my first topic, the research topic that I wanted to talk about. And the conclusion from this is that the substrate that we designed, which was made out of chitosan magnetic nanoparticles, vancomycin, was seen to be responsive to both magnetic and electrical stimulation. And the magnetic stimulation might sound like an alien concept, but right now, many research groups are doing clinical trials on the exact same concept, that we take this drug or drug substrate, we implant it inside the patient, and then we give it stimulation once in a week to make the drug release after every week. This has been seen to be very effective in the case of cancer or patients who need chemotherapy. So the DDS is always implanted as close as possible to the site where the cancer is. And doctors just go in once a week or whatever the particular dosage profile is, and then they give the stimulation. And electrical stimulation, while it is a very interesting proof of concept, it is not at a stage where we can do any sort of clinical trials yet. We were severely impeded by the lack of, we can say, by the lack of technological advancements needed in this particular area. So moving on to inkjet printed electronics. So as I was saying before, this is the inkjet printer. This is what a single cartridge looks like. The cartridge can have any sort of ink, and the ink just needs to fulfill certain criteria, that its viscosity would be certain amount, the size of the nanoparticles would be so and so. And once we are able to design that sort of ink, we can just put it in a cartridge and it's good to print with. The first thing we printed was capacitors. This was what the AFM image would look like. AFM is atomic force microscope. It gives you a nice image of the surface of any substrate that you want to test. And we printed various different kinds of capacitor, and this is what the plot looks like. So we were able to recreate, if I'm not sure, this is a lot of basic but involved electrical concepts. But capacitors have certain properties, and if you're designing capacitors successfully, you should see their properties fall on the same line, if you will. So as you change the area, the capacitance should change in a linear manner. We were able to recreate these results showing our first successfully printed capacitors. This layer between these two was a polymer called polyvinyl phenol, or PVP for short. And these two plates of the capacitors were designed with silver. And this is what it would look like. And these capacitors were flexible. So as you can see over here, we printed it on polyamide tape, and you can wear it on your wrist. This formed an important foundation for designing printable sensors. We designed this tuning coil as well. We designed resistors, and using resistors, capacitors, we designed this tuning coil, which could, and tuning coils are used when you want to wirelessly transmit data, for example. And after this, we tried printing some sensors. So the first sensor we printed was the humidity sensor, which you can see over here. So humidity sensor, in response to this person breathing, could tell you, or you could detect the person breathing, right? The blue graph that you see over here are the respirations that are detected by the sensor. So these are for 12 respirations per minute, these are for 30, these are for 60. So why this is a very straightforward sensor. And our hypothesis of why it works is that when we breathe on it, or when we exhale, for example, it deposits a very thin layer of humidity, or we call it the breathing sensor, but it's actually a humidity sensor. And when we inhale it, because of the draft of air, the humidity that's deposited on the sensor goes down. So because of this inhale and exhale action, the humidity on the sensor keeps changing. And as this humidity changes, the measured resistance between the electrical resistance between the two electrodes also changes. And that is what the device is measuring. So on inhale, it goes down, on exhale, it goes up, and so on. And the next important sensor we printed was ECG electrode. ECG stands for electrocardiogram, and it is something that you would use to measure your heart rate, for example. Or ECG comes into play to find out whether there's a heart murmur or a heart attack, for example, and so on. So we printed this electrode, and in response, this is with the response that we detected with our sensor, and this is the response that we detected with the electrode. That finishes my topic on printed electronics. Before I jump to the next topic, were there any questions on this? Okay. I'm going to briefly talk about the next one. This is a very big project that multiple faculty are across computer engineering department are involved in. So having lived in California, none of us are a stranger to wildfires. Wildfires happen every single year, right? And wildfires, they not only destroy a lot of wildlife, damage houses, like the Dixie Fire, for example, it obliterated entire cities. And although California has some attempts or some mechanisms in place to combat wildfires, they're obviously falling short. Right now, we have a wildfire that's threatening Sequoia National Park, and it has barely been contained. And there's only so much that fire responders can do. Once the wildfire has grown to become a very, very big size, it can no longer be controlled by water or with quenching chemicals and so on. So let me just briefly introduce the faculty. That's me, and we have professors from electrical engineering, from computer engineering, and so on. And we have a lot of community partners. We have council member Cynthia Moran. We have fire chief from Fullerton and Brea departments. We have the fire chief on board from Chino Hills. We have the second supervisor, Janice Rutherford from San Bernardino. We have the mayor San Bernardino as a part of this project. We have Carbon Canyon Fire Safe Council as a part advising us as well. So this is a very broad project that involves so many different personnel across so many fields of expertise. As I was saying, wildfires, we just see wildfires having an impact on the trees and people's lives around us. What we do not see being released from wildfires are copious amounts of carbon dioxide. And the carbon dioxide, which is the major greenhouse gas, is further causing the climate change to worsen every single year. So this is kind of a domino effect. You have wildfires releasing more carbon dioxide. Carbon dioxide are causing climate change and causing the Earth's temperature to go up. As the Earth's temperature goes up, we have more droughts. We have more dryness in the state. Like this is a very particularly harsh drought year. And again, that is causing more wildfires, more carbon dioxide, and it continues on and on every single year. California is also crossing its fiscal budget every single year that it allots for wildfires. I believe last year it spent somewhere around $736 billion, if I'm not mistaken. The last, and one single wildfire that lasts barely a month could release more pollution or carbon dioxide than that are released by all the vehicles in California in one entire year. So that puts in scale to things or how bad things really are. And this problem is particularly worse for Californians because 1/3 of the population lives close to an area that's designated as at a high risk of wildfire. So the state of current technology that we have in use is, first, we have a set of cameras. Like Carbon Canyon uses a network of cameras, and what these cameras do is keep taking images after certain intervals, and someone at the back end goes through those images and sees whether there are fires or not. The disadvantage of this is you always need a human somewhere at there going through dozens and dozens of images, seeing whether there's a fire or not. And where humans are involved, there we have a chance of failure, right? So, and also another issue is that the sensitivity of these cameras are severely impeded at night. Now, the next step from this was automatic image processing. So a research group wrote an algorithm and what that would do is take these images and run some AI algorithms on it to find out whether automatically find out whether there's a fire or not, right? And the disadvantage of this is that clouds and vegetation sometimes are misdiagnosed as fires. Like if you have clouds during sunset that look orange and very close to a flame, those are misdiagnosed as fires. Sometimes if you have vegetation that's has warmer colors during fall, for example, those are very easily misclassified as fires. Then we have satellite survey methods, in which case satellites make passes, daily passes over the state and find out whether whether there are fires or not. The major disadvantage of this is that there are several hours between each satellite pass. So in those hours, the fire may have worsened to an already uncontrollable state. If we talk about the fire that's near San Diego, I forgot the name of it. Within 4 hours, it had claimed around more than 12,000 acres, I believe. So if you had a satellite, right, it wouldn't have helped at all, because in the previous pass, maybe the satellite saw nothing. In the second pass, which is after like 6 or 8 hours, you already have a big fire that cannot be controlled. The next solution that some researchers also proposed is drone surveillance. So you have a network of or an army of drones that fly out over the area. They survey that area and see whether there are fires or not, and then they come back. The first disadvantage is that drones are very expensive. Each drone is around $1,000. So this, if you want to do like a big surveillance network, the cost becomes prohibitively large. You cannot have a lot of drones flying out. And even if you did, right, each drone can only fly for a maximum of 30 minutes. So it can only go so far in 30 minutes. And when you think about a very large, like Mojave, for example, or even Los Angeles forest, you cannot survey the whole forest in less than 30 minutes. And obviously drones again need a lot of human involvement. We do have volunteer fire programs like OC Firewatch, which do amazing work. But the disadvantage again of this is their visibility is limited at night. There are limited volunteers at night. You are putting the personnel at risk, and the people, they can only survey the areas that are urbanized. They cannot go out to the wilderness or very remote areas to see whether there's a fire or not. The next solution, the more effective solution, is creating wireless sensor networks. And that is the area that we want to focus on. Now, what the wireless sensor network would do, think of it as just a hub, right? And it has several different sensors on it. It has particulate sensors, it has smoke sensors, and it has temperature sensors. And these sensors, we program it, right? I do have had a prototype somewhere, I should have brought it. So these sensors constantly keep assessing the environment around it for certain data or values. And the moment it sees that the temperature went up, for example, or the particulates went up, right, it knows that there is a fire in that area. The moment a fire is created, in a few minutes, the node is capable of detecting that fire. And when it detects that fire, it sends a notification back to the fire responders. And the fire responders that then can immediately go in, and while the fire is young, it can control that fire, right? So these are the merits of our proposed technology. One, we are looking at smarter sensor nodes. That is the part I'm concerned with. Then also, once we implant these nodes, we want them to be independent, right? So for that, we want to equip them with solar panels. So solar panels would work in the daytime and charge a battery. The battery would provide the power to the nodes at night. And then we have a group of students also working out where exactly to place the nodes. Like each node has a surveillance area of, let's say, 500 meters around it. Now, if you're placing this on a flat surface, it is very easy to do. You put a grid line And you, at the corner of every grid or cell, you place the sensor node. But in a practical scenario like Carbon Canyon or Chino Hill State Park, you have a lot of valleys and hills. So those are going to significantly change the visibility of the nodes. You want each node to be able to see the other node so that it can propagate the data. So we are running some smart algorithms to explore that. We call it optimization algorithms with particle swarm optimization as an optimization technique, or Firefly, and so on. Now, once we have the data from the sensors, we might be able to predict which areas are at fire risk. And then once we tell the fire, the sensor nodes tell the fire responders that, okay, these GPS coordinates are likely to have a fire today, then the fire responders can go in and take some preemptive measures. Like maybe they have those chemicals, you might have seen those chemicals being sprayed from helicopters. So those are some preemptive actions that can be taken. And then once we have the data, right, we can make mathematical models that tell you which direction the fire is going to spread to once it has been created. And that is a very critical amount of information, because then again, it will help the fire responders at finding what strategies will stop the fires. Like if I know that a fire in a certain section of San Bernardino is going to spread towards this city. So then with that information, the fire responders can start taking steps that can block the fire, for example. And the last step, which another of our faculty team is working on, is mobile app support. This was an idea given to us by the fire chief. Most fires are caused by humans. And it's not just humans wanting to have a gender reveal party, for example, that starts a fire. Often in many cases, it is because of lack of awareness. Like there are things you can do to make your house safe against fires. There are things you can do to make sure that if there's a fire nearby, the embers from that fire does not put your house at risk. Or if your neighbor's house has a fire, it does not affect your house. There are things like that that the public needs to be educated about. So we want to design a mobile app along with several fire reach activities that will constantly keep reminding the public that this is a fire season going on, and these are things that you can do to protect your house, to make your surrounding more resilient to wildfires, for example. And also another aspect of the mobile app support is, if I am in an area that, let's say, has a fire, like Irvine routinely has a lot of fires each year. If a fire popped up, this mobile app would tell me what evacuation route to take. The evacuation route will be determined by the fire responders who are overseeing that area, and I can follow that route maybe as a Google map, on Google Maps, for example. If you look at the current evacuation protocol, they are just instructions stuck on a pole or an instruction stuck on a tree. And when a person is fleeing a fire affected area, it is not quite effective for them to expect them to look at poles or houses for or trees for instructions, right? So that is where the mobile app support comes in. We have made some progress on designing the sensor nodes. We have a prototype almost developed. What we are doing right now is trying to coordinate with, we obviously cannot create a fire in our lab, that is not too safe. So we are trying to coordinate with one of the fire chiefs so that they can provide access to our burn rooms. And then we would go into their burn rooms and test our prototypes. That's where we are at. And once that step has been successful, we will connect it with solar panels. And the solar panels, we have also thought about making it reconfigurable. What this means is the solar panels will be able to change its configuration in response to, let's say, something falling across it. If there's foliage or vegetation blocking a part of the solar panel, then the solar panel would still be able to extract the maximum power possible through smart reconfiguration so that the sensor node doesn't shut down. The goal being that once these sensor nodes are set up, we do not want people to have to go in for maintenance every year. Um, the benefits to society obviously would be that the early fire intention, the intervention will save a lot of life and property. If this method will or this mechanism will fulfill a severe knowledge gap in being able to detect fires right at the moment they are occurring, rather than waiting for it to become so big that it is only visually detected. And that is the point when people know usually that there is a fire. So it will also strengthen our support to firefighting efforts. Our firefighter efforts have been working very hard around the clock for hours at a time to firefight. And this would significantly help them in maximizing their efforts as well. This would also provide support of volunteer programs such as OC Firewatch and make them more efficient. We have plans in place to work with Fire Safe Council and help them, and they will help us, and we will help them recruit volunteers to use the apps and then support our firefighters with more effective firefighting. The project is very scalable. So once we show proof of concept in Chino Hills State Park, we have plans on implanting it in bigger areas like Los Angeles National Forest, for example. It also has benefits to students and CSUF. Right now, I'm working with 5 students on this project. My other faculty team are working on 2 students, I think. So 7 students are employed on this project. We recently filed a grant, and if that grant goes through, we will see active engagement of more students. So the more students we engage in research, the higher STEM retention rates we see. And the more chances we see of them graduating and moving on to a higher graduate degree. This is also a very unique project because it has a very strong collaboration between our community and the CSUF faculty, rather than of a project being limited by the boundaries of CSUF labs. We are looking forward to this project. We feel that it will have a lot of, it will take care of a lot of practical implementations. It will be a big benefit to the society, and it is also the need of the hour. We are almost at the end of phase 1. Actually also finished phase 1 and almost started phase 2. So we expect that once the grant funding rolls in and we are ensured a continuous flow of grants, by the end of next year, we will be able to have working prototypes or not working prototypes, implantable models for the sensor nodes and the mobile application. And with that, I set aside the last 20 minutes in case someone has any questions or wants more information on a specific topic. Thanks for your patience. You're muted, I think, Janice.
I'm sorry. So thank you. You've given us so much information. My head is spinning.
I know, I'm sorry, it's a lot of information.
No, that's what we've asked you to share with us. And may I just say that it's exciting to hear about your projects and the fact that they're viable solutions, potential viable solutions to these huge challenges that we see in the future. So it's so refreshing to hear from our young professors and understand what their research and how they're involving their students, and it's exciting. And I know that other members of the audience probably feel the same way. Do we have any questions or comments at this time? Let me pull up our Okay. I think they're slightly intimidated. So,
Sorry.
no, absolutely. This is what we look forward to is being educated. You know, the several of the things that you've touched on, I'm going to need to think about them more and understand and really look at your slides so I understand the points, the important points. Um, Irene Borden, she's chatting. She says she thinks she saw some news. Um, Let me pull the chat up.
Yes,
I'm sorry.
I
Okay.
saw her question too. Yeah. Yes, this is actually, you must have seen this on Fullerton homepage. This is a part of the ECS Big Ideas. So 6 faculties put in their big ideas last year and 3 were selected. Out of this was one idea.
Okay. So what Irene was saying is she did see news, local news about one of your ideas.
Local news, which paper? I did.
She says some news feature, and it could have been in
Hmm.
the Orange County Register or maybe the Titan.
I now remember that they talked about it on OC Register. Wow, I did not know they covered it on television. I'm not sure if they were talking about the same thing.
Okay. All right,
So.
great. Okay, just so do we have any other questions out there, audience? I'm not sure if we were able to facilitate a microphone in the Mackie. I know that there are people there trying to do so, but I don't see any. In fact, I don't know how they would do it, but since they are live on campus from the Mackey, we talked about the possibility of questions coming from that area or that
Uh,
channel of
oh, hi,
communication, but I
Janice.
don't see how that happening.
Hi,
So
Janice.
actually, if there are no other questions,
Hi,
I
Janice.
think we'll let you go and continue with your day. And thank you very, very much,
Thank
Ankita,
you.
for an enlightening
Hi,
presentation.
Janice.
My pleasure.
Oh, wait, excuse me. I'm sorry.
Oh,
Someone's speaking up.
Oh, hi, Janice. It's Renee. I'm at Mackey. We just wanted to say this was a wonderful presentation. It was interesting about all the little nano antibodies and oh,
Okay, Renee. Renee, you're breaking up. You also have an echo, so there's more than one device that's running.
no worries.
Okay. So, Ankita, could you get your team to work on this with Zoom? So we don't have the echoing going on when you have more than one device in the room. Uh, I'm sorry, Renee. Thank you for checking in, but we the echoing is a bit too bad, and it's the audio is breaking down. So thank you again, Akita,
my
and
pleasure.
we will hope to see you in several years as you stay with us as faculty and develop your research.
Thank you so much. It was great talking to you all. Thank you. I appreciate all of your time.
Thank you.
Thank you. Have a nice day.
Bye
Bye.
bye, everyone.